equation was x squared plus y squared plus z squared equals 4, right? That's what it was. What if I said take a cylinder and pass the cylinder through your sphere somewhere? It would cut through, wouldn't it? And it would create like a little path on top, like a little ellipse or something on top, or a circle on top, yes? And you would have another one on the bottom where it cut through. And now my question is, what points on the intersection of these two surfaces, on that little thing and on that, which points on those things are closest to this? Understand? So the way this works is that you have two constraints now. You have to live on the sphere, that's your first constraint, but you also must live on something else, which in this case would be a cylinder. And then Lagrange has a way you do that. The Lagrange method for this is that you set the gradient of f equal to, well, this part is exactly the same, right? Lambda times gradient of g, but then you say plus another constant, mu, times the gradient of h. How many equations will you get from these right here? You get 3 from this, and then 4, and then 5. You'll have 5 equations. You're solving for x, y, z, lambda, and mu. 5 equations, 5 variables. 5 equations, 5 variables. Would you like to see one of these? Yes. Okay, let's pick one out of the book. And I think I'll do a word problem if I can find a good one. And I just hope it's not going to be too hard. Okay, yeah, this one looks okay. I'm going to do the example right out of the book. That way we're playing it safe. Okay, so what we have is we have a function. The function we're given here is x, y, z is x plus 2y plus 3z. It says find the max of this, okay? Find the max of this function on the curve of intersection of the plane x minus y plus z equals 1. That's the equation of a plane, isn't it? Okay, and the cylinder x squared plus y squared equals 1. Okay, so geometrically, if I can try this, what we have is a cylinder, okay, right there, and we have a plane. I thought I saw a bunch of other colors in here. Let's see, red, try this. We have a plane, right? And we're assuming that this plane comes through and cuts through this cylinder, right? And creates, wow, that's terrible. Just say it cuts through somewhere, all right? And where it cuts through, it creates a curve, doesn't it? And there were problems that we had in the past where you were asked to find the vector equation of the curve, right? Intersection of two things, and you did that. What we're trying to figure out, though, is that if you take just the points that live on this intersection, these all have x, y, z's. You take each point and you plug them into that function, what's the biggest value you're going to get out? So your domain is actually just the points on this curve. You're constrained to that intersection, but you're plugging those into this function. What's the biggest thing that comes out? All right, so understand you have two constraints then? All right, let's write down, let's call this one G. The left side's G. This one is H, isn't it? And so let me write down my equations. The first one, I need the partial of f with respect to x to be equal to. Let's see if you can pick this up without me really giving you time to write any of that stuff down. That has to be equal to lambda partial g with respect to x plus mu partial h with respect to x. That's the first equation I'm going to have. Second equation. Partial f with respect to y plus, sorry, not plus. Partial of f with respect to y equals lambda partial g with respect to y plus mu partial h with respect to y. The third equation, yes?
Is lambda multiplied across for g of x and h?
Nope, it's just lambda times the g. That's it. And this is just mu times the h. Okay, third equation. Partial f with respect to z, lambda partial g with respect to z, plus mu partial h with respect to z. What's the fourth and fifth equation? The constraints, right? So I'll say that this one right here is 4, and this is 5. We okay with that? All right, let's see. I'm hoping these are going to turn out to be nice. What is the partial of f with respect to x?
1.
Yes, 1. Lambda times what's partial of g with respect to x? 1, so that's just lambda, isn't it? Plus, what's the partial of h with respect to x? 2x, and then times the mu. So it's going to be 2 mu x. Is that okay? Next one. Partial of f with respect to y. 2 equals lambda times partial of g with respect to y. Negative 1, so negative lambda. Plus, okay, mu partial of h with respect to y. 2u mu y. We good? Third one. 3 lambda. Oh, we're so lucky right now. What's partial of this with respect to z? 0, right? Plus mu times 0, but that means that's gone, which means lambda's 3. And once I know lambda's 3, I can come back over here, right? If lambda's 3, then this really becomes 3, then move it over to the other side. This is negative 2 equals 2 mu x, which means negative 1 equals mu x. Okay? If lambda's 3 here, you get what, 5? So you get 5 equals 2 mu y. And then this one, we don't even care about that, right? Now what? Solve for what? Okay, if you solve for mu, you're going to have to promise me something, though. You got to promise me x and y aren't 0, right? That's okay, though, right? Because what? You'll never satisfy equation 5 if x and y are both 0. Yes? So I'm going to just pick up right here. Suppose x and y are both not 0. Then equation 1 tells us that mu would be what? Negative 1 over x. And then equation 2 would tell us that mu is 5 over 2y. Now you can set those equal to each other, right? So you get negative 1 over x equals 5 over 2y. And do your little crisscrossy thing, however you want to do it. Negative 2y equals 5x. So we have a relationship between x and y, don't we? How about I solve this for y? Y is negative 5 halves x. Are you all good? Okay, what should I do with this? Take that to the fifth equation, right? Because if I have a relationship between x and y, this equation happens to have x and y in it, right? So I should be able to solve for x here. All right, so I'm going to go to equation 5, continuing here. In equation 5, I can rewrite that as x squared plus what's y squared for us if y is this? So 25 fourths x squared must equal 1. So what is that? 29 fourths x squared is 1. X squared is 4/29. And so finally, why is that cursor get down there? Get up there. X would be plus or minus 2 over root 29. All right, so I have to look at both of those cases now, don't I? So suppose x is positive 2 over root 29. What's y going to be then? It's right here, right? So what would happen if I do that? I do negative 5 halves times 2 over root 29. I just get negative 5 over root 29, right? What's that?
Negative 10 over.
Yeah, I reduced it. So I have x and y. Solve for z. Where? Fourth equation, right? If I know x and y, I can get z, can't I? So now I'm going to go to the fourth equation. Fourth equation is going to be 2 over root 29 minus y, but y is already negative, isn't it? So won't that be plus 5 over root 29 plus z equals 1, root 29. So z looks like it's going to turn out to be 1 minus 7 over root 29. And you could get a common denominator stuff, but I'm just going to leave it like that. That's z. So I found an x, y, z, didn't I? So it appears that 2 over root 29, negative 5 over root 29, and 1 minus 7 over root 29 is one place of interest, right? Now, I could go and try and find out well, I know lambda is 3, right? I could go figure out what mu is, but I don't need it. Here's x, y, z right here. Now, I also need to look at what? Negative x, right? So how would that change things, right? We would have some different results. And then you take those answers and you plug them into the original function to figure out the maximum. Do you think you can handle it from there? Yeah? I did say suppose that x and y were both not 0. So if x and y were 0, equation 5 wouldn't work, you'd be done. That's example 5 on page 682 if you want to see what the final answer is for that, all right? The homework for this section is, I changed it, where is it? There it is. That has the correct page, and it has the corrected numbers you should do. I did a couple of those on video. They're online. We good? Yes.
I didn't see the homework.
I just put it up this morning. Yeah, I think I did numbers 1, 5, and 13. Let me see. 1. Yeah, I think that's what I did. I will warn you though, number 7's a little tricky. The algebra of 7 is a little weird. If you do wind up getting into some trouble on 7, I'll refer you back to, let's see. Well, maybe not. Just see what happens on 7. I thought I had some work in here that might help. All right, that's it. We good? We can close the book on chapter 11. And now we begin chapter 12. We only have 2 more chapters. We're halfway there. We've done 10 and 11, right? 12 and 13, the book, we're done with the book. What? That sound good? All right, so now we're actually going to do some integration. I know, you know, like it's going to start to look a lot more like Cal 2 for a while now, all right? Until we get to chapter 13, which will still be integration, but it'll be a lot different, all right? So we'll be in vector fields and things like that instead of this stuff. So if you liked Cal 2 and integration, got good news. All right, so I put here in Cal 1, we learned that area under a curve is a Riemann sum. That might have happened in Cal 2. It might have never happened. I don't know. It depends on how you got here. But there's this thing in Cal 1 or 2 called the Riemann sum. And it was the way that we found that the area under a curve was tied to the integral, the antiderivative. So do we all understand that you have a function from a to b? If you want to know the area, then you have to find the antiderivative of little f. So that would be integral a to b of that function. Whatever the antiderivative is, you plug in b, get a number, plug in a, get a number, subtract the 2. Yes? It's Cal 2. Where this comes from, okay, the idea behind this is that this, why is my cursor, whoa, ah, shit. I hate Windows, man. Does these stupid updates. Can I stop it? Freaking Windows, man. I knew earlier, too, because it prompted me, and I told it to postpone. Okay, well, while it's doing that, I can't even get that to be white screen now.
You want to see the notes?
No, yeah, I know. I want to show everyone that, though.
I have to during Cal 1. It just restarted. I was laughing at it. I told him, dude, hey, there's an update. And he's like, no, I'll do it later.
What's that? Yeah, okay, that's a good idea. How about that quiz, the mini exam that is supposed to be a presentation? Remember that thing? I handed you in the first day of class? First or second day? Nobody has brought it up until today. Saying, hey, what about that thing, you know? So here's what I'm thinking, because I was hoping that, you know, throughout the entire semester, every week, I'd have a student or two in there doing some problems. Not the last, like, 4 weeks. Everyone's trying to rush through it. So what I think I'll do is I'm going to offer it as a, not a bonus, but as a way to replace your lowest mini exam score. Okay? But that means then it's going to have to be a little bit amped up. It can't just be like the easiest problem. I'm going to give you a thumbs up or down on whether or not you can do that problem. So you need to approach me I'll make it individual. You don't have to do it in group. If you do it in group, great. But individually, you have to approach me, and you have to say, hey, I would like to do this problem, and present it to you, and you can show me your work, and I can say, yeah, it looks good. And it'll probably take a couple of meetings, maybe 2 or 3 meetings between us, and then you'd present that, okay? And I'd like to record it. So if you're up for that, then let me know. If you're not, then it will not hurt your grade if you don't do it. Questions?
So it has to be a problem out of the book, or
No, it has to be a mini exam problem.
any exam?
Yep. All right, so while this is almost done here, the idea behind this area under a curve, the Riemann sum, how many of you saw Riemann sums? Like you saw it a little bit? Okay, some of you have not. The idea is that if you want to approximate the area under here, what you're going to do is you're going to imagine having a rectangle in here, and we can find the area of that rectangle. And if I get more rectangles in here and add them all up, then that would give me an approximation of the area. And it would be off a little bit because I'd always have a little bit of error in here, right? I'd always be a little bit off. But the more rectangles I had, the closer my answer would be to the correct answer. So the way we look at this is that the width of each of those we call delta x. That's the change in x. The height of this right here is just the function's value at x. And that's the area of one of these. And if I want to add them all up, it's the height times the width, right? That's the height of the rectangle times the width. And if I let there become an infinite number of these, right, an infinite number of rectangles, this symbol becomes an integral symbol. This stays the same. And this delta x becomes the differential dx, which is an infinitesimally small width. So that formula is directly related to this right here. Yes? That's all you need to know. We're not going to get into like hardcore Riemann sums by hand. I'm just trying to remind you of where that came from. All right, great. I thought it would give me another warning, and be like, hey, would you like to? Doesn't like that. There's so much crap running in the background, it's taking forever for this thing to remember who it is. Maybe it's a sign we should call it a day. It's too much for one day. All right, here we go. So we have the Riemann sums. So the total area, like I just said, okay, total area, you take a summation symbol, you basically let there be an infinite number of rectangles, and it becomes this integral symbol instead. Here's a picture of what I was just saying. And the more rectangles you have, the closer your estimated area gets to your true area. But that's Cal 1/2. We're talking about something else here, all right? But we're still looking back in Cal 1 right now. We were about to look in Cal 2. Remember that in Cal 1, or Cal 2, when we were doing the integration, can I just say Cal 2? This is more Cal 2 than Cal 1. Okay. the domain, right? That little dx, the little change in x, the width, came off the number line. It was this piece right here, right? That's our dx down there. And so the domain was a number line. And so we were looking at the interval AB, weren't we? Looking at this interval just between here and here. What's the area? And what we did was we picked some point, any point, didn't matter where it was, any point inside that rectangle, plugged that point into the function. That's what this says, hard to read it, f of x sub I. As long as you pick a point inside this interval and plug it in, that height will work. Because the more narrow your rectangle gets, that point basically converges down to one. It can only be one value. So that's the idea from Cal 2. We are interested now in looking at trying to find what are called double integrals. And so instead of looking at the area underneath the curve, we want to look at the volume under a surface. But do you see the similarities in it? Okay, so we're going to try it using Riemann sums. So here is a surface. No, there is no surface there. There is a surface right here. And I'm trying to find the volume underneath it, right? So what I do is I cut up a bunch of rectangular boxes, and I try and find the volume of each of these boxes. And if I could find a formula for the volume of each of those boxes, I would just add them up, wouldn't I? If I add them all up, I'd get an approximate volume. Do y'all see the connection here? Now, if I do more little boxes, right? Smaller and smaller little rectangular boxes in there, I'm going to start to get closer and closer to the true volume, right? And the way to actually get the true volume would be to let the number of those go to infinity. But that means turning a sum into an integral, right? So let's try and see if we can come up with a formula that would give us a volume of each of like an individual box. And this is my best rendition of it. First of all, since we're looking at the ground, right? This is a three-dimensional drawing. Here's the ground. Our ground is going to be a rectangle. All right, and we're just going to look above that rectangle up into the surface. So this is us looking straight down on that rectangle. If I pick some little dx, remember dx came off the x-axis? Some little dx, and I pick some little dy this way, I create this little box right here. If I pick some point inside that box, it would have both an x and a y coordinate. I'm going to call it x sub I, y sub I, and I plug that into the surface, it will pop up and it will be some value, and that will give me a height, won't it? And the volume of this is what? Length times width times height, right? So isn't it, this is the height, this is the width, and the height. I mean, sorry, length and width, right? So that's the volume of one of those little guys, and I want to add it up forever. But the thing is, you have to do a double summation. And the reason you have to do a double sum is, let's say you fix your dx this way, and then you start moving this way. So you take a sum in this direction, but you also have to take a sum in this direction. You have to move your x's over back and forth and your y's back and forth. So it becomes a double summation, right? It's the limit as you let the number of these rectangular boxes go to infinity of a double sum, which creates a double integral. And then this right here is this formula converted over. Do y'all see that? And that's it. That's how you find the volume. It's our formula. It's what we're going to use for the rest of this section. Okay, so if you're trying to find the volume between some surface, f of xy, and the xy plane, which would be the ground, over some rectangular region. Now notice the way that we write the rectangular region. We write the closed interval AB cross CD. It's not a cross product, okay? That's just the way we write a rectangular region in R2. Then it's given by this double integral. Now pay attention to this. Double integral over R. R is what? R is the rectangle, right? the double integral over R of f of xy. This right here represented what part of the picture? The f of xy was the height, right? So this was the height of it. This right here, D capital A. What do you think the capital A stands for? Area, right? It's an infinitesimal area on the ground. If I go back to that picture, this right here, that yellow piece right there is delta x times delta y. That's a little area on the ground, isn't it? So that is actually the dA. And now if I just change that over, this is what dA is, right? dx times dy. Or it's this other formula. What's the difference between these two? Let's see. This one, let's look at this one. If we work from the inside out, the inner integral, which I mean right here, the limits of integration are c and d, aren't they? C and d are your y values, aren't they? And I'm integrating with respect to y. Then I have an outer integral, which takes this answer and integrates from a to b and with respect to x. And that's because x corresponds to the AB, right, the x-axis. I could, though, do it the other way around. I could change the order. I could go from a to b, do it with respect to x first, take that answer, go from c to d, and do it with respect to y. All right? Both of those are at your disposal to use. You get to pick which one. If you're integrating over a rectangle, and only if you're integrating over a rectangle. In the next section, we integrate over more complicated regions, and you can't just switch it up whenever you want. So the rectangular region to integrate over is the easiest out of all the regions we're going to integrate on. So how do we integrate something like I just said? How would we do this integral on the inside? According to what I'm saying here in the notes, if you're going to take the antiderivative of a function of two variables with respect to y, you're going to treat x as a constant when you do your antiderivative. Just like when we did with partial derivatives, we're doing basically like a partial antiderivative now. We're going to hold one constant and go backwards. So the inner integral is this one in here. Since it's with respect to y, we hold x constant. And then on the outer integral, once we get to the outer one, x will be your variable. This one, it's the other way around, right? We're going to integrate with respect to x first, then we're going to hold y as a constant. Once we've done that, then we integrate with respect to y. You just got to see these in action. I think it's time for an example.